So we've seen how to do mole-to-mole conversions from reactants of a chemical reaction to see how much product that we're getting. But we know that there's also a relationship between the mass and the number of moles of molecule based on the molar mass, because the molar mass is given in grams per mole. And so this gives us a conversion factor to convert from mass to mass from a reactant to a product, because in the lab we measure in grams, so we have to know how do we convert. If I have a certain number of grams of a reactant, how much product do I get in grams? And this tells us that we can start, if we started out with mass A, then we can figure out what we can convert to moles of A using the molar mass of A, and then we can use our chemical equation here, our balanced chemical equation, to go from moles of A to moles of B. And this is the key point here, is the balanced chemical equation. We use the coefficients from there to figure out moles of A to moles of B. We can't go directly from the mass of A to the mass of B because our balanced chemical equation gives us a ratio of moles, not mass. You have to make sure you understand that. It gives us a relationship between the moles of something. That's why we have to go to moles of A, and then from moles of A we figure out how much moles of B we have based on our balanced chemical equation. And then if we want to convert to mass of B, then we use the molar mass of B to go back to the mass of B. Okay, let's go ahead and do an example. How many grams of glucose can be synthesized from 58.5 grams of carbon dioxide in photosynthesis? And we give you the balanced chemical equation for photosynthesis as here. And remember, we have grams of carbon dioxide first, but we can't go directly from grams of carbon dioxide to grams of glucose, because this relationship here is mole to mole. So that's why we have to first go and convert to moles of carbon dioxide. And then after we convert to moles of carbon dioxide, we can use our coefficients in our balanced chemical equation to figure out how much moles of how many moles of glucose we're producing. And since we want the answer in grams, we go ahead and we convert the moles of glucose into grams of glucose. All right, let's do that. So we have, our given is 58.5 grams of carbon dioxide, and we know that for every 1 mole of carbon dioxide, there's 44.01 grams. And you can look that up on the periodic table and figure out the formula mass for carbon dioxide as we've learned previously. All right, now we know that now we can use the chemical equation to determine the ratio of moles of carbon dioxide to moles of glucose. So we have 6 moles of CO2 for every 1 mole of C6H12O6, which is glucose. Okay, great. Now we are not finished yet, because if we finish, then we're just giving our answer in moles. We want to do one more step because we want our answer in grams. So we use the molar mass of our glucose, which is B in the flow chart that I showed you before. So 1 mole of glucose will have 180.2 grams. And this, of course, is its formula mass for glucose that we calculated. All right, let's cancel these out. And we're left with grams of glucose. And we make sure that we round to the correct number of significant figures. We put our unit of grams, and we put what it is, grams of what, which is grams of glucose, and that's our answer. Okay, let's do another example. One of the components of acid rain is nitric acid, which forms when nitrogen dioxide, a pollutant, reacts with oxygen and rainwater according to the following simplified reaction. And we have this reaction that is balanced, assuming that there's more than enough oxygen and water, how much nitric acid in kilograms form when 1.5 times 10 to the third kilogram of NO2 pollutant? Okay, here we start out with 1.5 times 10 to the third kilograms, right? And we say, okay, let's just use the molar mass of nitrogen dioxide to figure out the moles of nitrogen dioxide. But remember, the formula mass is given in grams per mole, and our unit here is kilograms. So we have to get rid of the kilograms first and convert that into grams in order to use our formula mass, right? So we know that for every 1 kilogram, there's 10 to the third, or 1,000 grams, right? Now we can use our formula mass for nitrogen dioxide, right? So we know that for every 46.01 grams, there's 1 mole of nitrogen dioxide. Okay, now we can use our balanced chemical equation to relate the moles of nitrogen dioxide to the moles of nitric acid produced. So we know there's 4 moles of NO2, not 4 grams of NO2, 4 moles of NO2 to make 4 moles of nitric acid. Great. But we can't stop there because we wanted our answer in kilograms. So let's go ahead and use our formula mass. We know for every 1 mole of HNO3, which is nitric acid, we have 63.02 grams. The problem is if we stop there, then we get our answer in grams, but we want our answer in kilograms. So we have to take it another step. We have 10 to the third, or 1,000 grams for every 1 kilogram, right? And so let us simplify. All right, our kilograms cancel out, our grams cancel out, our moles cancel out of NO2, our moles of nitric acid cancel out, our grams of nitric acid cancel out, and we're left with kilograms of nitric acid. Another thing that we can tell is this is a 4-to-4 ratio, so we can just simplify it as a 1-to-1, right? And then we see that we have 1,000 here on the top and 1,000 on the bottom, so we can simplify that too. So all you have to do is plug in 1.5 times 10 to the third times 63.02 divided by 46 in your calculator. So we're just cleaning up and simplifying the math. And we get 2.1 times 10 to the third kilograms of nitric acid produced. Remember, correct number of significant figures, units, and what your answer is. Okay, now you go ahead and you give this a try. Calculate the amount or the mass of carbon dioxide emitted upon the combustion of 5.0 times 10 to the second grams of pure octane. And remember, octane is in our gasoline, and when it explodes with oxygen gas, it gives us carbon dioxide and water. And this is the neat stuff about stoichiometry and relating reactants to products. How do scientists know how much carbon dioxide there is in the air? We don't necessarily have to measure it with an instrument. We can calculate some of the man-made emissions of carbon dioxide based on how much fuel we are producing. So if we are producing and consuming a certain number of tons of fuel, then we can use this chemical formula and others, of course, to figure out the theoretical amount of carbon dioxide that we have in the air. That's the point of stoichiometry. So go ahead and give this a try. And you always want to start with what you're given. So we have 5.0 times 10 to the second grams. Oh, and I want the mass in kilograms, please. All right, so we have 5.0 times 10 to the second grams of octane, which is C8H18. Now, let us convert the grams to moles so that we can use our chemical equation. So we have, for every 1 mole of octane, we have 114.23 grams. Okay. Now that we have moles of octane, we can use the coefficients here to see how much carbon dioxide we're getting from that. So for every 2 moles of C8H18 or octane, we get 16 moles of carbon dioxide. All right. Now we have moles of carbon dioxide, but we want it in kilograms. But before we can go to kilograms, we have to use our formula mass, and our formula mass for carbon dioxide is for every 1 mole of carbon dioxide, there's 44.01 grams. Now we take it one more step and we convert the grams into kilograms. For every 1,000 grams, or 10 to the third grams, there is 1 kilogram. We can simplify all this, cancel everything out, and we are left with kilograms of carbon dioxide. We should end up with 1.5 kilograms of carbon dioxide. The correct number of significant figures, don't forget your unit and what your answer is here.